Het aan te zetten. Oké, ja. Goeie... is het te hard? Een beetje, hè? Sorry?
Heeft u wel slaap blijven?
Ik niet. Waarschijnlijk niet. Maar misschien praat ik iets zachter. Is dat oké? Oké. Nou, goedemiddag. Good afternoon. I'm happy to see so many faces to talk about my favorite subject, of course. Black holes are very attractive, as you know, in all aspects. And that's something that really drew me into astrophysics, because when I was sort of starting my studies, and for some of you this is longer ago than me, and for many of you it's sort of less long ago than me, but you know, we still remember when we started our studies. There are certain things that you worry or think about, and to me it was always gravitation. You know, what is the nature of gravitation? Where does it come from? And it's still one of the biggest questions today, how to rhyme gravitational forces and how to rhyme quantum physics with each other. And that is, you know, and as long as there's something unsolved or unclear, or you can't bring two things together, there is still a mystery that promises some new insights. And so I always wanted to go to near black holes because that's there where gravity is the strongest. And the hope is that eventually we'll learn something new, something that we did not expect. For now, you know, black hole gravity is being successfully and completely described by Einstein's theory of general relativity, and that has passed all tests with flying colors so far. And so we always try to prove Einstein wrong, but we have not succeeded. And we try harder and harder. At some point, he got to be wrong, but we are not at this point because, again, as I said, you know, either quantum physics or general relativity have to be changed or modified or wrong at some point. But that point may be very far away, or we may be close to it. So only experiments will really show. Now, let's talk briefly about black holes. Of course, black holes, as you all know, are not holes at all. They are holes, well, they're holes in space and time. That's what you could say. But in principle, they are dense concentrations of matter. They can be formed in two different ways. The normal one is by an explosion of a very massive star, which then, you know, leaves a remnant. Initially a neutron star, you'd think, but then the mass, the gravitational attraction is so strong that even the degeneracy forces inside a neutron star cannot keep the neutron star alive. It will sort of collapse under its own pressure, and then the basic idea, it keeps collapsing because there's no force that resists, and you essentially collapse to a point source. Now, if you look at the very simple law of planetary motions, for example, around the sun, laws of Kepler and that were found many hundred years ago, then they described, and you can derive them from Newton's law of gravity, that the rotational speed around a point mass is equal to the square root of gm divided by r, where g is the gravitational constant, m is the mass, and r is the radial separation towards that point source. So what does that mean? Of course, the higher the mass at a fixed radius, the faster you rotate around it. And the closer you get, the smaller r gets, the larger v becomes, and becomes faster and faster. That's why the inner planets rotate much faster than the outer ones, also in terms of absolute speed. And that, of course, runs into problems as soon as r becomes very, very small. At some point, you reach the speed of light. And that you can just calculate. You put here c and then solve for r, and then you find that the gravitational radius, where sort of this becomes speed of light, is gm over c squared. And so this is a fundamental scale where something has to happen, because there the rotational speed becomes, you know, speed of light. It would be larger than speed of light, and Einstein has forbidden that as well. So he's a very strict person. He said, you know, nothing can go faster than the speed of light. In fact, light always goes with the speed of light. That's the very fundamental basis of all the theories. And that works amazingly well. And so something else must happen here. And that something else is then called the event horizon. Namely, at this point, the inside of that region is causally disconnected from the outside. Because, in order to get to the outside, you'd have to run faster than the speed of light, and that's not possible. Nothing can go faster than the speed of light. It's like having a waterfall, right? If you have a slow river, you can swim against the river. But if you go close to the waterfall, at some point, the river goes faster than you can swim, and then there's no way you can escape from the waterfall. You go down the waterfall, and once you're in there, there's no way to get up unless you take the stairs and you survive or whatever. But, flowing and swimming through the waterfall is impossible. So at this point, no information whatsoever can escape. Quick question, but... No, this is very simple Newtonian. So you have to make, I'll come to that, but I will not show the equation. This is the only equation I will show. And so the only, actually there are much more complicated equations that we are actually going into even that figure there. And so the relativistic change, of course, or the change that Einstein made was actually reinterpreting gravity not as a force, but as a curvature of space. And that had a lot of consequences. So if you imagine sort of space is curved, so matter actually curves space, and light still goes with the same speed, then actually light has to go sort of a longer space, so to speak. So if you measure time, actually time should move differently. And it turns out time will actually go slower as you go closer and closer to that point mass until the point that it actually comes to a standstill exactly at this point near the event horizon. Time seems to come to a standstill. For an observer, that is outside. If you are there, your time remains always unchanged. You always have your own time. It's always the relative time to the outside world that changes. So someone that sees you falling into the black hole will see you, going slower and slower. And so if you're twin brother, that's this old phenomenon. One falls close to the black hole, manages to come back through some magic or some, physics. Then they'll have different ages. And we see that actually on Earth through, for example, the GPS system, where there are very accurate clocks in space. They are further outside from the gravitational potential. They run a little bit faster than the same clocks here on Earth. And you have to correct for this, otherwise GPS wouldn't work. We'd be off by 10 kilometers after one day if we would not correct for these general relativistic corrections, that time runs differently. So we measure this essentially every day. We use that fact in our life. And so if you just extrapolate, you'll find, okay, if I make it very extreme, the Earth very small, like to 2 centimeters, then the time will come to a standstill. Also, light, of course, has to go through curved space, and then it will be actually deflected. And that's what you see here, plotted by these light rays. And what you see here, light, okay, goes around through the curved space. So, the laser beamer would go, would come back to me at some point. It even can go backwards, so to speak, as you see here. And the reason is that if the black hole rotates, it will actually make the space rotate with it. And so then the easiest way for a light ray to go around is actually go with the flow of space-time around it, and then enter the black hole here. You see something else, and that is that the color changes. It goes here from blue or violet or purple color, blue, green, eventually to red. So the color changes. And that has to do with the fact that the light has to climb out of the potential well of the black hole. It has to sort of run uphill. And we all know this. If we run uphill, we'll turn red. And okay, you don't know. You're Dutch. So you always give the in Netherlands. It's like cycling against the wind. Okay, then you turn red. On the other hand, we're in Nijmegen, so actually it's the only place in the Netherlands where people actually know, what it is too. No, but the reason is, of course, that you lose energy. You have to, you lose energy while you're climbing up this potential well, and then, a red photon has less energy than a blue photon. So you give up energy, and that is expressed by making the photon, redder, the wavelengths longer and longer. And in the most extreme case, a photon that emitted like an X-ray photon at the event horizon will be stretched to like a radio photon to something that's almost DC standstill. That would be exactly at the event horizon. So that would be the very extreme case. So these are all the effects that you see. This is something you can easily predict. Oh, one other number which is interesting. So if you calculate what this gravitational radius is, it's 1.5 kilometer for our sun. So if you compress the sun to 1.5 kilometer radius or 3 kilometer diameter, then it would be a black hole. Our Earth, like 2 centimeters. If you go to a black hole of mass of 100 million solar masses, which actually we think we see in the centers of galaxies, that's actually quite typical for larger galaxies. Then you'd have 150 million kilometers, which actually is the size or the distance from the Earth to the sun itself. So, you know, the black hole, the event horizon, will fill the entire region in between the sun and the Earth's orbit. If you then look at what the average density is, it's the mass divided by the volume, you know, with 2 Rg cubed, then you find that the average density you need to create this is of order grams per cubic centimeter. And if you remember what that means, it's sort of a kilogram per liter, or 2 kilograms per liter, so to speak, which is the density of water, right? So, you know, if you keep your faucet on when you go on vacation, and you know, and it keeps pouring, it keeps filling the entire solar system with water, you turn out into a black hole. So you know, it's much more dangerous than leaving the iron on, which, you know, puts your house on fire only. That's okay, but, you know, flooding the entire solar system with water would actually turn us into a black hole. Of course, you have to have enough water, right? So which is a problem because a huge amount of space in there. But so it's for supermassive black holes. For very large black holes, the density is doesn't need to be that extreme to make it. Of course, that water will still collapse into a black hole, become smaller and smaller, and probably become dense again. But this is something we cannot see because it's inside the event horizon, right? So that's what we would not see. So that much about the theory. Now, of course, then you want to know how it looks like. And now this is how it looks like. This is actually, if you go to the movies, the movie Interstellar. In fact, they did some effort to actually ray trace properly how a black hole looks like, though the overall model and some aspect of this are actually not quite accurate, and they're sort of, you know, made to suit the Hollywood needs. But in fact, this is actually not very innovative. If you go back to the very first papers that were used to actually calculate how a black hole looks like, this is sort of goes back to the 70s, and people didn't have big computers then at their fingertips. So what we see here is a calculation how a star that orbits around a black hole would appear on a camera. So the star moves around these various points, and then it traces out this structure. And what you see here really very much resembles the you know, much more fancy computer graphics of the Interstellar movie that came out 2 or 3 years ago. And what you see is, of course, are the effects of light bending, you know, because the light is bent around the black hole depending on where you are, and the effects are much stronger here, that you get this deformed view. Now, this here is, for example, a disk which is more or less in the plane of the sky, but then behind, of course, the light is bent around the black hole, and so you see sort of part of the back of your head, so to speak. If your head would be a black hole, you would see sort of part of your, which could be useful in the morning, actually, but might also be painful if it feels like a black hole. But anyway, so that was one of the first calculations. What actually struck me more was this paper by Bardeen in '73, which was a very unnoticed conference proceedings, where he was sort of asking, how does a black hole look like that stands in front of a star? Let's assume a star, an extended star, passes behind a black hole. What would you see? And in fact, what he found that there's sort of a large radius outside the black hole. This is the event horizon, where photons are actually captured, and then they are sort of ending up in the black hole. So this lensing effect means that even a much larger area is cut out from the light behind, and you actually would see a hole in the star, which is actually 10 times the gravitational radius I just mentioned. I call it gravitational radius. There's also a Schwarzschild radius, which is factor 2 larger. So it would be 5 Schwarzschild radii or 10 gravitational radii. So that's much larger than the event horizon. That is very crucial, because that actually turns out is something that makes it possible that we today could actually image black holes with a radio telescope. This is something we're actually attempting, which I will explain in the future, or in the next coming minutes. Now, this here is a simulation we did actually 17 years ago, we published, which actually got the whole show started. And that was the assumption that, okay, it's very unlikely, and this is talking about the black hole in the center of our Milky Way, which I will introduce in a moment, that it never happens that a black hole passes in front of a star and you can see it. I mean, this would be so insanely small, and you have so few cases where this is, it's almost impossible to ever see this. Maybe in hundreds of years when we have gigantomanic telescopes, which in extreme sensitivity, we know exactly where to look, and maybe. But not for the foreseeable future are we able to see a black hole in front of a star. But what we do see, we have a very massive black hole in the center of our Milky Way, which is surrounded by a fog of radiation. And I'll come to that. And if we have that situation, then the same happens again. This light bending actually punches out a dark region, which is 10 times the gravitational radius, so much larger than the event horizon. And that is something you could see. And so that got us actually all very excited. Now today, of course, we actually do much more sophisticated simulations of black holes. This was just assuming there was some fog around it. Today, we actually use essentially supercomputers to calculate the fluid dynamics around a black hole. So what you do is you put a dense material around the black hole. This is sort of done here. So this is supposed to indicate the black hole. This are density contours, and this is a thick torus or ring. What's also important, we thread this with magnetic fields. This is indicated by those lines. And those magnetic fields are very, very crucial. Because what now happens is that the disk starts to rotate around the black hole. And the magnetic fields are actually stretched and extended. And that leads to some form of an effective viscosity. So you break, essentially, part of the material. This one goes faster, this one goes slower. So you break stuff. And actually, as you move slower, it falls towards the black hole. So that's how an accretion process starts. Material flows towards the black hole, and the magnetic field lines are being tangled and wrapped around. And that's what you calculate. You take the equations of fluid dynamics, you add magnetic fields, and you look how this develops as a function of time. And a nice accretion flow established, plus something else, and this is something I've been working on for quite some time. Namely, those magnetic fields in the inner region are actually spun up, and then actually they escape at the inner region. A large fraction of the magnetic field is able to escape in this corkscrew fashion. That's sort of, you wind it up, and then in the inner region, sort of part escapes. So it's like a slingshot. And that will take along some actually material that flows out. And this is something that we can see. Now, what you've seen here is a simulation of how the density looks like. You have to also add how does the radiation look like, because radiation will be created, and that's what you really look at. You don't know how many particles there are. This is a simulation of a black hole. And what you see here is sort of the radiation. You see sort of the accretion flow going around the inner regions. And you see, in fact, here going north and up and down, this emission from this plasma sheath that goes out, this jet. And in fact, we see that in real life. This here is a picture of a galaxy of 1 or 2 giga light years away, billion light years away. And this is an elliptical galaxy with sort of many hundreds of millions to 1,000 million stars, a billion stars. And sort of doesn't look that spectacular. But if you then switch on a radio telescope and overlay this image, you see something really beautiful shooting out of this galaxy. This is sort of, it looks like how the guys called who spit fire. But anyway, so it's huh? En? Ja, vuurspuger, maar ik weet niet, I forgot the name in English. So yeah, it really looks like someone spitting out fire here. And in fact, you can actually measure individual features sometimes very close in. You see that this material actually, is traced back to the center of the galaxy. Most energy comes from a region smaller than the solar system. It has an energy which is actually more than the entire galaxy. So many hundreds to thousands of billions of stars being produced coming from a region which is as small as a solar system and actually moves with close to the speed of light. And so that's really telltale signals so that it comes from something that is very realistic. Typically the escape speed, the speed of such a flow is related to how much the escape speed is near the surface. And that has to be an object where the escape speed is close to the speed of light. Another example is this one. This is M87, a galaxy actually not that far away. There are nicer images of M87. This is at 17 megaparsecs, so this is roughly times 3. So about 50 light years, so 50 million light years away. If you look at this in the optical, there's actually a little feature here which we don't see right now, but sort of not that spectacular. But if you look at the radio at the same scale, you see actually it's completely filled with a plume of radio-emitting material. This actually was made in the Netherlands with the LOFAR telescope, which is in the Netherlands. You see stuff going out. If you then zoom in, you see actually that this comes from, there's this fast outflow in the inner region. If you then zoom further in, you see that this goes down to here. And there is indications from the motion of stars that there is a dark mass of about 2 to 4 billion solar masses in the very center. And so we are getting here to like tens to hundreds of the size of a black hole already with measurements in the radio. And so that's a very interesting region to look at. And we can model this. So this here is a larger scale model of the similar simulations I showed before, where actually the emission is mainly coming from the radio jet. And you see a very nice, like this corkscrew pattern. It's actually a little bit like a sand clock or whatever. So most of the emission really comes from the outer edges in this simulation. That's the same you see here in these VLBI observations. These are sort of averaged over multiple years. You see that most of the emission is actually concentrated in the outer edges. So that very nicely resembles the simulations that are now naturally emerging from our computer simulations. And in the inner region, it's dark because it starts being absorbed by the accretion flow. I think this is one of the nicest images I've ever seen, made by Monika Mosiborska here in our university. Now, of course, if and that was sort of the finding from the finding of quasars more than by now almost 50 years ago, and many studies thereafter of galaxies. There's always some evidence for a really dark mass concentration in the center of galaxies, and that was explained by supermassive black holes producing a lot of energy in the very center of galaxies. And if that's the case, then there should be one in the center of our own galaxy as well. Now, this is another galaxy, but just to, because, we can't see our own galaxy from the outside. We are sitting in it, but this is a real radio image made with the Effelsberg telescope in Bonn, actually. Shows, a very bright region in the galaxy. You saw before there was this galactic disk, and it was dark, and that's because there was a lot of dust. There's a lot of dust in the center of the Milky Way. But radio penetrates through the dust, and we can see all the way to the very center. And that's what we're doing here, zooming in. The central region here is called Sagittarius A. Much nicer images now. This is actually an old movie I made when I was sort of a postdoc still. And then we're going to zoom further into the radio structure, and you see this structure, Sagittarius A, resolved much better. This outer part is Sagittarius A East. This is Sagittarius A West. This is probably a supernova explosion. This is sort of some streamers of gas that are sort of going into or around the central region. It's moving with like 200 kilometers per second around that region, and we actually see it move. We see that gas move after 10, 15 years. It actually moves around the black hole. So we know the speeds are really high, and that indicates there's sort of about 1 million, 2 million, 4 million solar masses matter in the very center to make it move that fast. And in the very region, we see this radio source, which is called Sagittarius A star. Sagittarius A, it was called Sagittarius A because it was the brightest radio source in the constellation of Sagittarius. And then the star was added to indicate it's a very exciting object. So, because, you know, in atomic physics, star were excited states. And so people said, like 40 years ago, this is very exciting stuff, so we call it Sagittarius A star. So that's what got people very interested, seeing this radio source, this very compact radio source in the very center of the Milky Way. Now the same in the optical. Now here you see again a zoom into the center of our Milky Way with an optical telescope. You see all these dark regions which are molecular clouds. They're dust, and out of this dust actually stars form, and they block our view of the center and the optical, as I said. But then 20 years ago or so, well, in the early 90s, good infrared near-infrared detectors became available, which you usually use as heat cameras. But also near-infrared emission is able to look through the dust. And then you see a new world, new stars popping up, a really dense concentration of stars. And if you zoom into the very center, less than a light year from the very center, the galactic center is like 24,000 light years away. This year is less than a light year. And what you see is all the stars move, and this one actually has moved on a elliptical orbit around a particular point, and that particular point is that radio source Sagittarius A star. So all the stars actually move. They all move on elliptical orbits. They all move around that radio source. And some of them move with 10,000 kilometers per second. And so from, again, Kepler's law, you can derive how fast they move, how far they are away, so how strong does the gravitational attraction have to be. It turns out to be 4 million times the mass of the sun has to be concentrated in that particular point in that radio source. And there is, the light that comes out is like 100 times the light of the sun, not 4 million times the light of the sun. So it's a relatively dark region, it's almost invisible. Occasionally we now see it flicker. But nothing like 4 million suns, and certainly not on this scale. And by the way, this one star who has been going around had made actually one turn already. It's now on its way to its second turn. It takes like 15 or 17 years to go around. And actually this May, it will do its second turn around, swing around the black hole. It will go very close and swing around. And people in Garching, actually near Munich, Reinhard Genzel and others, Gillis and Eisenhower, they have actually a very fine near-infrared interferometer in Chile where they combine 4 large telescopes into an interferometer. They can measure very precisely that position. They can see that star now move every day, and they'll trace it as it goes around in May. So that'll be very exciting unless there are clouds in our atmosphere, but I hope that's not going to happen. Okay. So that's what we know about Sagittarius A star. Let's see how I'm doing at time. Maybe I should move a bit forward. Well, I'll still explain this graph here. It's this is a frequency here, frequency axis, and this is the intensity of radiation coming from that very central region. And what you see here is that the intensity of the radiation increases in the radio regime. So this here is, well, it actually should start here, is sort of 1.5 gigahertz or so. This is where the cell phones work, or 2 gigahertz. The microwave here is in this regime, a few gigahertz. And then you go to like 40 gigahertz. This is a satellite communication, hardly used in daily use. And then here we are where we have this airport scanner. In Germany, we call it the Nude scanner because it looks through your clothing and sort of up to the skin with very small wavelengths, millimeter size wavelengths. And what you see is intensity increases, and then suddenly it drops. It stops. You know, it goes higher and higher, and it stops. And we made a model of this. We said this actually emission comes from the stuff that flows out. And if you make that model, you find that actually, if you're outside from this plasma jet, from this black hole, or from whatever produces it, you get low frequencies, red colors. If you go to higher frequencies, so higher frequency colors, like in the radio now, yellow, green, or blue, you get closer and closer to the black hole. And the region where you reach here, the millimeter waves, a few around terahertz or submillimeter, that's actually where you reach the event horizon. And so we were saying that as you go higher, here you actually disappear essentially in the black hole, and so you can't go to higher frequencies. That's why it cuts off. And so what you have to do in this regime, you have to look at the black hole, because that's where the emission comes from, very close to the black hole. This is the magical frequency to look at. And that's what we're doing. And these are simulations actually we've made for this source. This here is actually at a low frequency. This is sort of where the satellite communication at 43 gigahertz is happening. So you see this, in our simulation, you see this jet flowing out, you see the stuff going around. But actually, you don't see the black hole in there. And that's because it's optically thick. The emission is made really on further out. Only if you go to higher frequencies, you're essentially able to look through the gas, like X-raying, but then X-raying with higher radio frequencies. You actually can zoom in, and you actually start seeing the hole appear. And that's what you want to look. And this is at a frequency of about 230 gigahertz. You see actually the hole appear. Now, people have made measurements of this source in the very center, of course. These are sort of the images that we have available. This is at 8 gigahertz, so this is sort of a lowish frequency, a little bit above your microwave. It's actually a big blob, okay? So, of course, you don't see the black hole. Now, then you go to a higher frequency, and it still looks like a blob, but it's smaller, okay? Then you say, okay, we have to go to a higher frequency and see how does it look like. And it still looks like a blob. When you go to a higher frequency, it looks like a blob, and then it still looks like a blob, until about sort of 90 gigahertz radiation. This was very frustrating for 30 years. People would only see sort of a blob. And why is this? Well, it turns out that the radio emission that we see is actually blurred by our Milky Way. There's some gas, there's some electrons in the Milky Way, and they blur the image of the source. So what we see is not the source itself, it's sort of like looking through a milky glass. So you don't see any structure. Very frustrating. But actually, you can show that as you go to these highest frequencies here, the source becomes, this scattering effect becomes less and less, actually becomes smaller than the size of the event horizon. So another reason why you should go to the high frequencies. At lower frequency, it would be completely blurred. Only at 230 gigahertz, you can see the event horizon. That's really a fortuitous coincidence. It's very nice that God placed the Earth exactly at this location, because had it been much further away or at a different location, the source would have been completely blurred at 230 gigahertz. And even though we could X-ray through to the event horizon, we wouldn't see anything because it would be completely scattered. So exactly at this magical frequency of 230 gigahertz, the emission comes from the event horizon, and the scattering is not important. And as I will explain in a moment, the Earth is just large enough to give us a telescope that is sharp enough to actually see this shadow in the center of the Milky Way. I'll skip that here, these figures. So how do we do this? Well, as I said, you need to see this shadow. It's several, like 50 million kilometers in diameter, but at a distance of 24,000 light years. And so it will appear as the size of a mustard seed in New York as seen from Nijmegen. So that's how sharp an image you have to make. So mustard seed in New York. And actually you need to see something on the mustard seed in order to see it. And so you know which wavelengths to look at, and then the resolution of a telescope is given by the wavelengths divided by the size of the telescope. The wavelength is given, it's 1 millimeter. 1 millimeter divided by, how large a telescope do I have to have in order to see a mustard seed in New York? It's about 15,000 kilometers. So actually you need almost the entire size of the Earth to get that telescope. So nobody will fund that, but nobody will like that. Occasionally we do have, it would be good during rainy days, right? So it would cover all the rain. But during sunny days, we would still like to see the sun. So bad idea. But what you can do is you can actually combine telescope over the world, and actually you make a virtual telescope the size of the Earth. And in principle, how this works is like a double slit experiment. If some physicists are around, this is sort of the waves that come in. And then you measure only the waves here and here. You combine them. You get sort of some kind of interference pattern. And depending on where that source is, that interference pattern will actually slightly shift. Sometimes you have a maximum, sometimes a minimum, and that's very sensitive to where that source is. So you can, within sort of a wavelength, you can measure this, and that can give you very precise measurements of where the source is. And if you combine multiple telescopes over the world, then actually you can very nicely localize where that source is, and you can actually even make an image. So you make a virtual telescope the size of the Earth by combining telescope all over the world. Now you need a few of those, and so that's why it took a while to get there at the high frequencies. At low frequencies, it's actually already quite standard. And so at high frequencies, this had been very difficult because there weren't so many telescopes. One problem is that the atmosphere absorbs this high frequency radio emission when there's a little bit of humidity in the air. So water absorbs this. That's why sort of the scanner at the airport, it sees through to your skin more or less, but then it's absorbed. It goes through the dry clothing a little bit, but not all. And so you have to go to high mountains and have very precise radio telescopes. So the first detection of Sagittarius A star, the first measurement, showing already that the emission comes from very close to the event horizon, was done here between a mountain in Grenoble and in Spain, in this Sierra Nevada near Granada. A mountain is called Pico Veleta. So that was the first detection. And then on the American side, there were 3 telescopes, one in Arizona, one in California, and one in Hawaii, which were combined and made many measurements and confirmed that and made it better and showed that really the emission comes from very close to the event horizon, but it wasn't able to make an image yet. Because with just one baseline, as we call it, one direction, it's impossible. You measure information, structural information in one direction, but you cannot make an image. You really have to probe all directions. And that you can do by adding more telescopes. There's a paper now in preparation where we added one telescope. People in Bonn, particularly, added the telescope in Chile. And now we made a global experiment with a large collaboration of 150 scientists all around the world, with 6 mountains and 8 telescopes on 6 mountains here in Spain, Arizona, Hawaii. California, unfortunately, was dismantled. A new telescope in Mexico, a big telescope in Chile, which was very important, the ALMA telescope, and indeed a telescope on the South Pole. And they all observed the galactic center last April for a number of days, and the data is now being processed, and we know it looks very good. And so with this data, we should be able to make the first rough and crappy images, at least, of the galactic center. So I'll take you along a little bit in this enterprise. So this year's telescope in Mexico. In fact, there were students from and staff from our university at essentially all telescopes except South Pole. But it turned out that actually at the South Pole there was a guy from Amsterdam who was actually wintering over there. So there was a very good Dutch present in this experiment. This is a telescope in Arizona, in Chile, actually many telescopes combined, and then the South Pole, which of course is the most spectacular one. I show you here pictures from a previous experiment where I went up to Arizona. You go up to 3,000 meters with your 4-wheel drive. You get a little pickup car like this for one person. It's very it's low density, right? The air pressure is low. You see your chips are inflating when you take them along, because you have to. There you actually have to take care of your own food. This is the Arizona mountain peak. This is the telescope here. Actually, it's inside a housing. This is actually the large binocular telescope. There are 2 8-meter mirrors combined. This is campus police because it's part of the University of Arizona campus. So they have to watch out for you. This is the telescope when the dome is opened. This is the secondary, which actually wobbles around when we are not doing VLBI to make on-off measurements. This is sort of the control room, and my job is just to keep the operator who is doing most of the work awake. And actually next to this is also the Vatican Observatory. So when we're not observing, you can actually go to the Jesuits and have a nice chat with them, or beer, whatever. I don't drink beer, but some people can have beer there. Then the last year I was going to Pico Veleta, to the Spanish telescope in Granada, up there. just to give you a feel for how this goes. Again, you're taken up in a car by the IRAM crew. This is actually Thomas Krichbaum who made the very first measurement published in '98. This is actually a ski resort. Up there is the telescope. I think the telescope was, well, ski resort was there also in the early days, but it has grown a lot. The telescope has stayed there. To make the last mile, so to speak, you have to take a little car like this. And so they have their own hobby, how they call it. Anyway, so then these are the group of observers who are going up there to the telescope. Again, Thomas, station manager in the back, some scientists, a crew up on the mountain. This is the ski area, and there you see the mountains. The telescope, 30 meter in diameter, doing actually lots of different signs, and only a few days a year it's doing VLBI. This is our VLBI equipment. These are all hard disk racks, so everything that's blinking here, actually each of these blocks had 6 or 8 terabyte hard drives. In total, there's up to 1 petabyte of data per telescope that we write the data to. And then later, the data is brought to correlation centers where it's then combined. So we had, the last run, we had 4 to 5. Looks like a U-boat, by the way, the inner part of this telescope. It's German design. So it was built by the same companies, right? So, and so this is the receiver cabin. The light goes through here. It's actually, that's a chopper which rotates. This is the receiver itself. So it's actually very, very complicated equipment itself. This is the atomic clock. All of the telescopes have an atomic clock. This was an old one, the oldest one. This is now replaced. And the good thing about IRAM, Picovillator, it actually has fantastic food. So they cook for you. The only telescope, I think, where they do this, where they really make wonderful food. Yeah. These are the other crews here. This is at ALMA. Guys from Max Planck. This is Chiriaco, who's working here at Radboud. The guy from Haystack Observatory. That was before the observation. This was after the observations. It's very tiring. You have to spend a couple of 2 weeks on the mountain. Yeah. Of course, then we already have our first result that I posted very quickly after the observations. This was sort of found by an operator. So this is, of course, remember the theory from the Hollywood movie Interstellar, and this is sort of what we found. This was found by the brown hole. Actually, I was posting this on Twitter, and someone was asking, so is this real or is this not? I said, no, it's a cup of coffee. It really is a cup of coffee. But anyway, so yeah, but it looked stunning, right? So I thought this was one of my most watched tweets, I think. Now, what do we really expect? Now, the opinions differ a little bit. These simulations we did, taking all effects into account, it could be that on the first observing run, all we see is something like this, just a few ugly blobs here, right? The reason is that the source changes and the scattering medium changes, and so it becomes difficult to image. We don't have that many telescopes. However, if we add number of years, we should be getting something like this. I call this an ugly peanut. And that would be sort of the first indication that we really see the edge of the black hole, the edge of the event horizon. We could actually measure how large it is and compare it to the predictions of Einstein. That we could measure this to about 10%, we think, after a few years. So that's interesting. That would be like the first stepping stone to do this experiment, but we want to do more. And so how can we move further in this enterprise? And then this is a current network. And I've put in a DREAM telescope, and the DREAM telescope is actually in Africa, because we have telescopes up here in South Africa, here and here, but we have nothing in Africa. And it's obvious there's a big gap that we still need. We need to have a telescope there. And so that will really fill in this plane and make many more connections and improve the imaging. And unfortunately, in all of Africa, there's not a single telescope operating at these frequencies, and most high mountains are in this region, but we want to be close to that coast. But there is a telescope that we can actually have. We even can have it for free. It has one disadvantage. It's a bit older, so it needs a little bit of refurbishment, but that's okay. It's still in very good shape, because the same type of telescope is operated in France by an institute for many years, so that actually is not a problem. Problem is it sits in Chile. So what we have to do is we have to move this telescope from Chile to Africa, in fact to Namibia, to do this. And that's what we're trying right now, trying to raise the money to actually move this telescope. We think that to move this and put it up there, it's about 1 to 2 million euros that we have to find. It's not a huge on the scale of things, but this money is really not available at this point. So we are trying to start a program, maybe even get money from private sponsors or from companies to actually, because it's going to be a spectacular move to actually a spectacular location. This is the Gamsberg Mountain, the second highest mountain in Namibia, which has an advantage that A, it's completely flat on top, and it belongs to the Max Planck Society. It was always meant to be an observatory. In the end, they always moved to Chile for various reasons, but the location is actually very good. It's actually close to Windhoek, so it's a very nice mountain and a very spectacular location as well. This sort of we've been there, and this is 3 kilometers long, 800 meters wide. You have a spectacular view into the Namib. So if you're from the Netherlands, you've seen enough of green. This is actually where you want to be. A lot of nice desert colors and really interesting structures. So we've been here on this. These are actually some amateur astronomers who put up their own little huts with little telescopes. They, their own telescope up there, yeah, just roaming around on the mountain is quite spectacular. Because it really, this cuts off. Actually, it once was the deepest point of an ocean. So everything else is eroded away. Only this deepest point has survived. So it's actually quite amazing how things change over time. There's a communication mast up there, and this is where we had actually lunch, which is a very nice lunch you can have up there. So, and we hope that in the end we're able to hear. This is a combination. If we have everything together, we could get something which is not an ugly peanut anymore, but maybe a sort of a nice banana. So that would we improve the image even much more over the next couple of years. Now, of course, you want to go even further. This would be nice. This will be spectacular. We think. We hope in a few years, maybe already this year. Who knows? But we haven't really looked at the data yet. But this is how the image would look like at 230 gigahertz. So that's the frequency we use right now. This is what is the optimal scenario you could get with a perfect telescope, because it's still blurred. But if you go to a high frequencies, so a factor 3 higher in frequencies, very short wavelengths, 690 gigahertz, for example, it will become much sharper, and the scattering doesn't change anything. So that's how the black hole really would look like. You would see like a very sharp sickle, like a quarter moon or so, and that you can test in detail this shadow idea. Well, but this frequency to do from Earth is almost impossible. There are few locations on Earth where you can do this. You'll never get enough telescope, enough time to do this. It's very difficult, and the atmosphere is very hostile. So this is, it's almost impossible. So you have to go into space, and so that's what we're proposing here. That you actually go to a height of 15,000 kilometers. You have 2 spacecrafts orbiting around the Earth, slightly different orbits. So the inner one will go a little bit faster than the outer one. And after time, this is exaggerated, they will drift apart and they will rotate around, and so you get all kinds of connections. You see, you have your small connections measuring actually large scales. If you go to, if they're far away, you measure actually the very fine scales, and you measure it in all directions. If you average this over a couple of months, you should be able to recover something which is really a nice, sharp image of the black hole. So that would be really, something. We could make it even nicer. We didn't put any effort into making this a nice looking one. So that's So I think seeing a black hole is actually not out of the question perhaps not even in our lifetimes. So images, the conclusion, images of the shadow of black holes will come sooner or later. I warn people, because there was an article in National Geographic, astronomers have made the first image of the black hole. They have taken the data. They have not even made the image yet. If they make the image, that will probably happen later this year. It will probably look crappy. It may not even be a nice image at all. But this will become sharper with time as we average and becomes better and better. And eventually we add, the Africa telescope, maybe even more telescopes in Africa. We go to space. We can really see black holes. And then, something that was completely invisible was something was just an idea, just a dream, right? Suddenly becomes a reality, becomes an image. I think that's what's so exciting about this. It has always been in our imagination, but we've never seen it. And so that hopefully can change soon. And then, of course, the next step is you will probe it with detailed tests of, you will test general relativity. Ideally, you hope that actually Einstein is not right? But my fear is he will be, So the old guy will have the last word after all. Now, the last thing I want to show you is actually some fun project I'm doing with with some of my people, and done by PhD students, and Monika Mosibrochka, our theory withered. And this is actually the path of a particle around a black hole. So it goes around, and then at some point it will actually hit it will close to this outflowing jet. Then it will shoot out. And so we'll follow how this particle goes around the black hole. This is still a sort of preliminary version of the movie, but let's look at this. So now we're going around it. We have no accretion flow. You see a starry background, and you see how we rotate around it. We keep rotating, so that's why the background moves. And now we actually switch on the radiation from the accretion flow soon. So you see the absorption. You see here what's called the Einstein ring. And now you see actually the glow in the radio. That would be how the radio would look like. In the optical, you would not see that much. Well, you would see a little bit. And now we also see the jet appearing. Now this is actually a virtual reality 360-degree view. So this is actually the pole, so don't be misled. This is actually just one pixel, right? You have to project this onto a sphere around you. So it's best seen, we have actually virtual reality glasses, so you can put this on your head, and you can actually then look around and see how it looks like to look at this black hole in all directions and so forth. And now we're actually leaving the black hole along the jet and going out. So this is, I think, one of the nicest movies made so far, but we're going to make better ones. And we're now talking with a company in the Netherlands who actually makes very nice planetarium movies. And we want to turn this into a planetarium movie that you can see in planetariums all over the world in next year, perhaps. So let's hope this works out. So thank you for your attention. So maybe some questions?
First of all, it was amazing. And I'm a chemist, I'm not a physicist. But you mentioned one sentence, you say, well, now we have all these data, and we start making an image of it.
Mm-hmm.
So, but I think you can make all kinds of images of it. It's a matter of how you will use the data. So how do you know that the image you create is the image?
Yes, a very good question. How do you, I have to repeat it for technical reasons. How do you know that the image we make is the right one? What we measure is actually components in the Fourier domain, each baseline. So what we actually do is a Fourier transform of the data. And then we have missing information, namely where there is no telescope. But in the Fourier domain, you essentially, you lose, it's like a JPEG, for example. I know in the old days, you would actually download an image from the web, and it would look first very unsharp, not very clear, and it would become sharper and sharper. That you do by throwing away information in the Fourier domain. You don't really throw away structural information, you lose sharpness, so to speak. So we actually can make an image, but as long as the image is not too complicated, we can still recover that. But then there's also a point of doing the right image processing. We check this by having 3 different teams, which independently have to look at the same data. At this point, maybe 2 in the end, we have to see. And that's the reason why we haven't looked at the data yet. We have looked at calibrator data, so at other black holes, where you do not expect to see the shadow. So we're first trying to verify that we can do this right. And then later we will actually look at the galactic center. So I'm glad that we've been able to install these processes, these procedures, which were not common in VLBI in this field for a while. But we think that given the uniqueness of this experiment, we have to do this. Yes. So we do a direct reconstruction from the Fourier domain, yes.
That needs an enormous calculating capacity.
No, actually, the amount of data that's left in the end is very limited because we actually, there's a 10 petabytes of data, or actually 5 petabytes, but this is because we measure sort of on, the raw data is measured on very high time cadence, nanoseconds, many fraction of nanoseconds you have data, but we average this over seconds and so forth. So you actually enormously reduce the data by a factor of many millions to a small data set. No, actually you can do this image processing you can do on your laptop. So the image I showed that was made for LOFAR, of this M87, was much more compute intensive. That was 10 terabyte of data and you needed a supercomputer, but had much more information. The one we have, because we have only very few telescopes, can be done on your laptop.
But you don't use tricks like constructing like in MRI apparatuses?
We use some image reconstruction techniques, which are probably related. I'm not familiar what an MRI image processing algorithm does. I think it has much more information than we have. But yeah, and you do use some assumptions about the image, that it's compact, that is regular on some scales, and there are different algorithms. Depending on what your pre-assumptions are, you get slightly different results. That's absolutely true. And this is something we have to quantify, how different a result you can get. Yes. So it's not perfectly unique. But let's first have some other questions, and then we can.
Can you indicate the mechanism, simple explanation, how the rotation of a black hole makes throwing out the jets?
Yeah. That's a good point. This is something we see all over the universe, that these jets come out. And essentially, I think it has to do with the inner boundary conditions. It's sort of, you stretch magnetic fields, and here they sort of run up to a wall, and then essentially pile up. And then they actually escape along the rotation axis, like a slingshot. Ways to explain this in intuitive ways are not easy, and there's still some discussions of what the actual effect is that makes this. There are a number of semi-analytic calculations why this happens, and we see it in the simulations. And sometimes, understanding what the simulations do is also not so straightforward.
Yeah. It was predicted long before it was observed, I think, or not?
No, the jets was the first thing that were ever seen. So I think that really co-developed this formation of jets. In fact, for a long time, it was very difficult to understand why these jets were launched. But now in the simulation, this almost happens naturally. You have to. Yeah. I have to think of a better way to explain this. I think it's a very good question. Yeah.
You have not mentioned something about temperature.
Yes.
Is it that in a black hole there's an extreme high temperature, or is it reverse, that is 0 Kelvin?
Both, in fact. The gas falling onto the black hole has a very high. The question was about temperature of black holes. The gas going around it has very high temperatures. So we have a billion Kelvin to a 10 billion Kelvin gas temperatures. So it's extremely hot. And that's what we see actually relativistic synchrotron emission. So electrons move with close to the speed of light in the magnetic field, and then they actually make radio emission. So the gas is very hot. If you have no accretion flow, nothing at all, then you can assign a temperature to a black hole. It has an equivalent temperature of a black body, so to speak. And that temperature is extremely low. I think it's way below Kelvin. I actually forgot what the temperature of that one is. It's extremely low. But that is what is responsible for the so-called Hawking radiation. Yeah, so you can assign a theoretical temperature to that body, and it would radiate. But that temperature is so much lower than anything else in the universe that for the foreseeable future of our universe, black holes will never really radiate. They will always sort of absorb radiation, at least those large ones. So that was the last question here then.
And another question. You mentioned that you hope that something is not perfect.
Yes.
I have do you have some ideas in mind, like boson stars or something?
Yeah, so the question, what would be alternatives? Indeed, there are people who suggest boson stars, which sort of you have a condensation not of neutrons, like a neutron star, but bosons, which sort of are able to, you could make a more stable configuration, but then you need a certain type of particle which doesn't really exist. And it's not able to explain all black holes. So every black hole, you have to have a special particle that you need to postulate. So it seems very contrived to actually, explain all the black holes with boson stars, because you have to, for every galaxy, you have to change particle physics. It doesn't make much sense. Who knows? But maybe there's some. I always say maybe green jelly has some weird properties at very high densities, so maybe it can survive. Who knows? We've never studied, like a jelly bean with 4 million solar masses. There's no known physics that could keep it stable. There are people who actually. So yeah, but let yourself be surprised by nature. More seriously, I would say people actually modify the equations of general relativity by adding additional scalar fields and so forth. That is in principle possible, and that could change the appearance of black holes. And if the effect is strong enough, the shape would look different. The question is, if those effects exist, and if they exist, on what level? How large does this parameter have to be relative to all the other parameters that we know already? And that's completely open. It could be a strong deformation of the shadow, or it could be a minute change of that shape that is impossible to see for any foreseeable future. So that's because it's complete speculation. For now, only observations can tell. Okay? So, do you want to?
Heino, thank you very much. I'll take you along to have some drinks. Will you join us?
Yeah, until 5. I have a very unpleasant telecon at 6. So.
Okay. Now, if there are no more questions or some questions you want to ask Heino personally, I'll say you can follow me back to the hallway where you have the coffee and tea.